Hello everybody, in this lecture we will be studying the number of essentially different colorings of the faces of a cube of let's change this, faces of a cube. It turns out that the cube is a platonic solid which is a dual with the octahedron, and as a result the number of colorings of the cube is of the faces of a cube turns out to be equivalent to the number of colorings of the vertices of an octahedron, and similarly the number of colorings of the faces of an octahedron is equal to the number of colorings of the vertices of a cube, and so on. It turns out that the number of colorings of the vertices of a tetrahedron and the number of colorings of the faces of a tetrahedron are equivalent because a tetrahedron is its own dual, and so on. And the other two remaining, the icosahedron and the dodecahedron, they also have colorings which are equal in terms of when you switch faces with vertices, because these are also duals as well. So going back to our situation, so we have a cube which have 6 faces, and we would like to color these faces using only 3 colors. So C is equal to 3, and in order to do that we need to first figure out the group of symmetries, right? So what are the members, the group members that will act on this shape? And so let's start. So we first have the identity, then we have a bunch of first of all, because this shape is 3D, three-dimensional, we will only consider rotational symmetries. It wouldn't make sense to consider reflections, so only rotations. So let's start with simple ones. Consider the axis of symmetry, which goes through the center of one face and it goes through the center of the other face, right? And so like that. And we have multiple rotations here. We can have a 90-degree rotation, a 180-degree, or a 260-degree rotation, 270-degree rotation. Let's call this axis as S. So we have let's call it ST. Let's just call it S. So we have S sub 90 degrees, S sub 180 degrees, and S sub 270 degrees. In a similar way, we can have an axis of symmetry going through like this. Again, rotations, let's call it T. So we have T of 90 degrees, T 180 degrees, and T of 270 degrees. What else? And then we have this one, the front side, through the middle of the front side to the opposite side, STU, let's call it U, U 90 degrees, U sub 180, and U sub 270 degrees. Okay, so what other type of symmetries do we have? So when I say symmetries, when the group member acts on this shape, it rotates it, but such that the cube shape is preserved in its original location. The faces can interchange, but the cube should remain the same from the angle that you are looking at. Well, another one would be the space diagonals. For instance, if you consider these two vertices which are opposite to each other in space, then let me represent them with a different color. Then if you consider this axis of symmetry, in fact, just to make it if I look at it from this is my eye, and if I look at it from this angle, what I would see would be something like that, right? So I would see the cube like this. So that's the angle that I will be seeing the cube from. So as a result, I realize that from each of these space diagonals, let's call this one, I don't know, V, let's say V. There are two variations. I can rotate it 120 degrees, or I can rotate it 240 degrees. So we would have V of 120 and then V of 240 degrees. In a similar way, I can take this guy with its opposite. There will be a symmetry axis here. I can call this one W. So we will have W of 120 and W of 240. And I would have two more pairs. So this guy and this guy here. VW, XYZ, and X of 120 and X of 240 degree rotation. And finally this guy and this guy here. Yeah, so let's call them Y of 120 degrees, Y of 240 degrees. And at this moment you might even think that we are done, right? So there's no other symmetries, but you would be wrong. The best way to know how many group members will there be on a 3D shape is actually very simple. All you do is you count the number of vertices, so that's very important. So the number of G is equal to number of vertices times the number of edges which emanate from one vertex, from given vertex. We see 1, 2, 3. So number of edges that comes out of a given vertex, right? So as a result, number of vertices here in this picture would be 4 plus 4, 8 times from each vertex we have 3 edges coming out, 3 here, so we should expect 24. So far we have 1, 9 more here, 10, and then 8 more here, 18. So we are still missing 6 more. Can you see where these 6 missing guys are located? Well, here, if you have thought about it, come on, help me here. Okay, so the missing 6 guys are here. Consider this the midpoint of this edge and the midpoint of this edge and this guy here, this axis of symmetry, and you rotate it 180 degrees here. Yeah, so it's hard to believe, but it is true. Yeah, so you rotate this 180 degrees, so I don't know, let's call it K, I guess. K 120 degrees. In a similar way, every opposite edges, the midpoints of these, for instance, this guy here and this guy, we have another axis of symmetry here. You rotate it 180 degrees, I should say here. L, let's call it L 180 degrees. And then similarly, this guy and this guy. M 180 degrees. And finally, which one is missing? K, L, M. I should have 3 more, right? Oh, well, all the remaining ones. I think one opposite to this guy, one opposite to this guy, and one opposite to this guy. Let's call them N, O, P. So N 180, O 180, and P 180 degrees. Whew, so we have the 24. The rest of the problem, so you might think, hey, this is crazy, but the rest of the problem is actually significantly easy. Once you establish this list, all that remains is to show the fixes in each one, basically counting the number of cycles that will come out of this, which is just a matter of simple calculation. So let me make it smaller, and let's begin. So the number of colorings would simply be equal to we have 24 symmetries, so 1 over 24, open parentheses. So the fix of the identity will fix, so each face will remain its same, and each face there are 3 different ways to color it, so therefore we will have 3 to the 6th plus, and by the way, this example is also listed on Wikipedia, so you can also check that as well. Okay, so let's consider S 90 degrees. So S was here, going through the midpoints of the faces, and when you do a 90-degree rotation, the top face will remain the same. That's the first cycle. The bottom face will remain the same, and all the side faces will switch by 1, so therefore that's the third cycle. So we have in total 3 cycles. Oops, 3 cubed. But then we also have, okay, so how about S of 100? When we rotate it 180 degrees, the top stays the same, the bottom stays the same, so far we have 2 cycles. Then this face is going directly opposite face, and this face going directly to the opposite face, so in fact we have 4 cycles in that case. 270 is the same as 90, so we have 3 cycles again. But then the others are just a replication of these, so all I do is I just multiply it by 3 plus, now let's go to the other business, so space diagonal. So if we have the 2 of these, then we can simply multiply it by 4. So let's do the space diagonal, rotated it by 120 degrees. When we rotate a space diagonal by 120 degrees, this face goes to here, this face goes to here, but these are 3 of the faces, 3 of the faces adjacent to one guy, 3 of the faces adjacent to that vertex. They will create another cycle, so in total we will have 2 cycles. The same thing will apply to the 240 degrees. This face will go counterclockwise to this one, to this one, to this one. Again, 2 faces, 2 cycles, I should say, and boom. And finally, these weird symmetries. Consider the yellow symmetry axis. You have the midpoint. So which face goes to where? Obviously, this is hard to explain. This face here, I hope you see it, will go right underneath, so these 2 will exchange. Actually, this face is sharing a common edge with this guy, which is just underneath, so these 2 will exchange. Then this guy here will exchange with the face behind, and so on. So in total we will have 4 cycles in this case. So 4 cycles for pretty much every single one of the remaining guys. So I hope that's clear. So therefore we have 6 times 3 to the power, 3, my bad, 3 cycles. This face will exchange with the face at the bottom, this face will exchange with the face at here, and then the front face will exchange with the backs. In total there are 6 faces, so 3 cycles, and that's it. That's just it. So all that remains is to calculate this number. You can, as I said, pretty much do it pretty easily. You can also check it on Wikipedia. I think Wikipedia says the answer should be 57. I'm kind of lazy to make the calculation, but I'm pretty sure this should yield the correct calculation. Now, just as a side note, if there wasn't 3 colors, but if you had a general number of colors, say C colors, in that case all you would do is just change these 3's with the letter C. So this way you would get a generalization, and generalization for the number of colorings for the faces of a cube. So I'll just leave it to you as a homework. One final side note, another benefit of using Burnside. Well, okay, so what's fancy or funny is that once you generalize this, so if for any number of colorings, it turns out that you will get a polynomial function, in this case a 6-degree polynomial, and you will easily see that this polynomial will be divisible by 24, because the number of colorings should always come out as a positive integer, right? So that's kind of very neat as a divisibility condition of polynomials. Just wanted to also mention that as well. So hope you enjoyed it, and just looking forward to see you guys in our next video.